So the answers to that little quiz, the assignment that we've done, it will be in the videos for the next class. Okay, so the next class, I'm going to do the same thing, but I'm going to go over it with them, and then you guys will see the recording of it. Well, that's the plan as of right now, okay? And if we have time, we might go back to it, okay? But I want to make sure we get to some other things that we need to discuss. So what if I did this? Okay, remember in organic chemistry, arrows are very, very important. So the way I drew that arrow right there is a resonance arrow. Now, and then let's change the problem, put a formal charge right there, +1. Is this a correct resonance arrow? And draw the product. Or not the product, but draw the second resonance structure. What if I take the pi electrons here and put them there? Is that valid? Can I do that? And what does the structure look like? I'll give you guys like 30 seconds. So what am I doing? I'm taking these 2 electrons in that pi bond. And where am I moving those 2 electrons? The arrow says I'm going to put them right there. So is that valid? Okay, is what I drew, that second resonance structure, is that correct? No, because I see a +1 charge over here, and this is completely neutral. I see that this carbocation right here has how many hydrogens? 1, so there still has to be 1 there. Did I break a octet rule with regard to that carbon? No, it has 4 bonds, so that's okay. How many hydrogens were here? Just 1, so there's still just 1 right there. So how many bonds does this carbon have? 3. Only has 3, so that means that has to have a plus charge. So that is a valid resonance structure because we have pi electrons that are adjacent to a carbocation. So those electrons can move. So we call that, these electrons right here, they're delocalized. Just another way of saying, hey, those pi electrons, they can move. What if I drew a structure like this? Would this be a valid resonance structure? The orange arrow is saying put the 2 electrons in between those 2 carbons just like that. Is that a valid, did I do that correctly? No. People who said no, why is that so bad? Texas carbon. Because this guy right here has how many hydrogens? 3. And in resonance structures, do we move atoms? No, we don't. So there's still 3 right there. And so clearly that's a Texas carbon, and that does not work. So if you ever have the question, like if you come to my office hours and you're like, Dr. Lawrence, can I draw this pi bond going over here? And my response to you will draw what the resonance structure looks like and answer your own question. And I'll poke at you and prod you like, is that valid? Do you see any problems or mistakes with it? So if you come across the problem and you ask yourself, can I move those electrons? Move them and see what happens. Does it violate the octet rule? Okay? So that is not a resonance structure. That cannot happen. What if we had let's say a amine? Okay, like that. Could we draw a resonance structure? Yeah, we can, because we have some lone pairs. Now let's compare. Let's do a comparison here. Goodness, what do I want to do? Okay, we compare those 2 molecules there. One you see a double bond, one you don't. This amine right here in black, what degree of amine is that?
Second degree.
That's a secondary amine. And what about this guy? Secondary amine as well. So we're comparing apples to apples the best that we can, except what's the difference? There's a pi bond. So these lone pairs in this guy right here, they're delocalized. And what does delocalized mean? They can move. Watch how they can move. They can come down like that and put the electrons on that carbon. I'm drawing the arrows exactly where I want you to see where the electrons are going. So this lone pair right there is going in between the nitrogen and the carbon. These pi electrons are going to go right on to the carbon. Now we have to reevaluate the formal charge. We have a nitrogen with 4 bonds. So that has to be positive. And now we have a hydrogen or a carbon atom right here with a formal charge of -1. Is that a valid resonance structure? And the answer is yes, it is. Because when you have lone pairs on a heteroatom adjacent to an alkene like so, you can bring them down and pop the pi electrons onto the carbon, just like that. So that is a valid resonance structure. But can I do the same thing with this other one? No, I can't. If I tried, what would we do? We're not breaking any single bond, but that is the way that I've drawn it there. What would that look like? We would have a double bond there. So that would be positive, and what did I form here? A Texas carbon, so that's not valid. Could I take this nitrogen and move the electrons this way?
Also no.
No, because you form another Texas carbon, right? So you notice, though, that these lone pairs, or this lone pair right there, they can't move. So they're localized. They cannot engage in resonance because they're just stuck there. And that has to do with everything that it's surrounded by is what is its hybridization state? What's that hybridization state of that carbon? sp3, that carbon, sp3. There's no p orbitals for the electrons in the pi bonds or the lone pairs to move around in. But when we take a look at this guy right there, that is, in fact, sp2. And so those electrons can move. So we have localized and delocalized electrons. They can be in lone pairs, delocalized, localized. We can also have them in pi bonds. Can I draw a resonance structure where I take those pi electrons and move them over there? Like that. How many hydrogens are on this carbon? 1, 2, 3. How many hydrogens are on this carbon?
Still 3.
Still 3. I just made a Texas carbon. You can't do that. So those pi electrons in this particular molecule are localized. They can't go anywhere. They're just stuck there. But if you change it up ever so slightly, get a vinyl cation or an allyl cation, can that take pi electrons and move it over like that? Yes, it can. And then the positive charge would be right there. So those pi electrons are delocalized. So when you're asking the question of are these electrons localized or delocalized, you have to look at the neighboring atoms. Very neighboring, or right next to each other. So what if I had something like this? This is a common mistake. Let's see here. Like that. Can I take these pi electrons and move them right there? No, you cannot. Because these pi electrons right here, they have to travel through orbitals, right? That's how they move. And so we have an sp2 hybridized orbital there, but what's the hybridization state of that guy? sp3. And then the hybridization state of that carbon is sp2. So these electrons in this carbon, they want to go this way, but they get stuck at this spot right there because there's no p orbitals for the electrons to flow through because it's sp3 hybridized. So many students, if I clean this up, will do this. They'll be like, I'll say, draw a resonance structure for this molecule. And they will go, boom, there's my resonance structure. We put the electrons there, and now the plus charge, they'll put it anywhere. They'll maybe put it there. That cannot happen. But if we change it ever so slightly and put the plus charge right next to it, that will work, okay? So let's come back to this idea of localized and delocalized electrons. And I know this is going to bother a lot of you, but truth is truth. I'm not going to sugarcoat it. It's just what it is. And if you guys can accept it, great. If not, then that's your prerogative, okay? So if we take, let's say, a amide, like this, okay? The way you've been taught up to this point, what is the hybridization state of that oxygen? What did you guys say? sp2. Okay. And then what would the hybridization state be of that nitrogen? How many groups are around it? 4 groups. So what would you say the hybridization state is? sp3. Okay. Now, amides and esters, what can they do? They can, that lone pair right there, that is delocalized. Because what's adjacent to it? A pi bond. So that lone pair can come down like this and go like that. And so when we draw the resonance structure, follow those orange arrows. What is it saying to do? It's saying we're going to put a double bond there. We broke a pi bond on the oxygen. And now, how many lone pairs were already there? There were 2 lone pairs. So those are the original. And then the pi bond that's being broken, those 2 electrons went there. So now, recalculate the formal charge. What's the formal charge on the oxygen atom right here?
-1.
That's a -1. And what's the formal charge on this carbon, or this nitrogen right here? +1. Beautiful. So that is a valid resonance structure that works. But now if we ask the question, what is the hybridization state of that nitrogen? How many groups are around it? There's 3 groups around it. So that makes that sp2. And then how many groups are around this oxygen? There's 4 groups around that oxygen, so that should be what? sp3. Do you see how it went from sp2 to sp3? And then sp2, sp3? Remember, going back to my analogy, if we have a purple mule that was bred from a red horse and a blue donkey, we get a purple mule, right? So does that purple mule say, I'm a horse today?
No.
You know, it can't. It is just a mule. So the same analogy applies to this molecule. That nitrogen is not saying, oh, I want to be sp3. I want to be sp2. It is just what it is. And that's really hard to describe on paper. What does that molecule really look like? So we do the best that we can. And so when I ask you that amide nitrogen, what is its hybridization state? You will always say sp2. Because it's this, when you take a look at it, both resonance structures, you're just going to take the hybridization state with the smallest number. So you see sp3 on the right for the nitrogen, sp2 on the right, or sp3 on the left, sp2 on the right. And so what's the hybridization state of the nitrogen atom? sp2. So what you have to be careful of is making sure that you identify your electrons as localized and delocalized. So if I give you this example right here, give you a alcohol right here, what is the hybridization state of that oxygen atom? Say it a little bit louder. sp3. There's 4 groups around it. Do we follow? Okay, so that's sp3. But if I changed it up just a little bit, now what functional group do I have? Carboxylic acid. What is the hybridization state of that oxygen? sp3, sp2, sp?
SP3.
sp3? Okay, by show of hands, how many think it's sp3? What about sp2? Wasn't it? Okay, you guys missed the lesson. You missed the lesson. I know I just taught it to you and then in 10 seconds I asked you to apply it, but you guys missed it. Now that, after I said that, reevaluate. What did you miss? You missed the concept, are those lone pairs localized or delocalized? Look at that lone pair right there. I can bring that down and resonate it. And when we resonate, that lone pair stayed. We form a double bond. So when we look at this one on the left, many of you said sp3 because there's 4 groups around it. But you didn't ask the question, are these localized or delocalized? They're delocalized, and so now when you take a look at that guy, what's the hybridization state of that oxygen? You clearly see that it's sp2 because there's only 3 groups around it. So what is the hybridization state of that oxygen atom that we're talking about? sp2 only. You could do that same analysis for this guy right here. There's 2 lone pairs. What's the hybridization state of that oxygen? sp2. But when we come over here, it kind of looks like it's sp3 because there's 4 groups around it. But what is the hybridization state of that oxygen? sp2, because there's resonance. There's delocalized electrons. So as you go through resonance problems, you're going to start seeing patterns. And if you guys purchased that paperback book that I suggested you get from Klein, what is it called? Organic Chemistry as a Second Language. Is that something? Am I saying it right? It has lots and lots of resonance problems that you could practice with. And they talk about and show you patterns that you can start recognizing. Okay, so let's drive this point home. Let's draw a ester. What is the hybridization state of that oxygen? sp2, because it's adjacent to a I bond. So the lone pairs on that oxygen, you can definitely draw a resonance structure. Those could come down, pop up. Okay? So that's localization, delocalization. And so now that throws you guys for a little bit of a loop.
You don't say.
Okay? But that's how it is. The hybridization state of an amide nitrogen is sp2. And you'd be amazed at all these years and how many times I will stand up on this desk and scream at you guys and say the amide nitrogen is always sp2. I'd say more than half of the class says sp3. So I wonder, why? Am I not clear? What's the hybridization state of the amide nitrogen? sp2. You all said it. So I don't want anyone getting that one wrong. Because I'm being very animated about this concept. Okay? Okay, the next question is that topic that we want to discuss is that we have resonance structures, and we can create many resonance structures for one molecule. But not all the resonance structures that you can create are significant. Some resonance structures matter a lot, And other resonance structures we don't even care about. But are they still there? Yes, but they're just less significant. So we have developed some rules to help us understand which resonance structures that we're looking at are significant or not. And so when you guys go to your textbook, you're going to see in section 2.11, it lists all the rules right there. And I'm not going to rewrite them out. I'm just going to talk about them. Rule 1, most significant resonance structures. Rule 2, Rule 3, and Rule 4. And we're going to go through these rules, but I'm not going to write down all the words. Okay, so when you go back to study, go to this page so you can see the verbiage, exactly how it's written. So as we go through this problem set here, let's look at rule number 1. Okay, and I'm just going to read it to you. The most significant resonance structure forms have the greatest number of filled octets. The greatest number of filled octets. So if we draw something like this, okay, we have a hydrogen there, that, and then we can draw a resonance structure. We can bring that down like so. And then we'll get something like this. When we take a look at those two resonance structures, which one is the most significant one? Let's read the rule again. The most significant resonant forms have the greatest number of filled octets. So what that's saying is you need to evaluate each atom. Does that have an octet? Yes. Does the oxygen have an octet? Yes. Does this carbon have an octet? No. Because we see a carbocation. So that means it's missing 2 electrons. So it only has 6 electrons around that carbon. This carbon here has an octet. So we see 3 checks and 1 X. Now we evaluate the other resonance structure. That works. Does that oxygen have 80 electrons around it? Yes, it does. It has a plus charge, but it still has 80 electrons around it. And then this carbon right here has 80 electrons around it. And same with that one. So you see the molecule on the right, all the atoms have a resonance or an octet. So when comparing the two, this one is going to be the most significant resonance structure. Because that's the first rule. Most number of octets. Now these rules, 1 through 4, you have to evaluate a problem in the order that I'm teaching you it. So you have to start with rule 1, look at octets. You will then come to a point where you're going to take a look at a problem and say, well, all the resonance structures have an octet. So let's take a look at something that looks like this. Draw a resonance structure. And then we have and let's see, what did we do? Like that. Okay? So when we take a look at these 3 resonance structures, we want to ask the question, which ones are, let's rank them, most significant to the least significant. So rule 1 states that we have to look at the octets. And so we see that there's a lone pair, octet, octet, octet. And I'm doing this rather quickly. Octet, octet, and octet. But then we come here, no octet on that carbocation. So right out of the gate, using rule number 1, we can say of these 3 resonance structures, this one is the least significant. Because we have one atom that does not have an octet. But now you have the molecule in the middle and the one on the left. Rule 1 doesn't help us because all the atoms have an octet. So we have to generate a second rule. And the second rule states the structure with fewer formal charges is more significant. So we're just counting how many formal charges there are. This guy has 0 formal charges, and this guy has 2 formal charges. It has a positive and a plus. So between those 2 resonance forms, rule 2 says this is the most significant. You see how I broke that tie there? Well, I had rule 1, there was a tie. They all have octets. Rule 2 says, look at how many formal charges there are. And the one with the least amount of formal charges is going to be the most significant. Does that make sense? Okay. Let's see. If we come into a situation where we have something that looks like this. Okay. Which one is the most significant between these 2? Well, we have to start with rule 1. Octet, 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 octet. Octet, 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 octet. Okay, so rule 1 does not help us. What does rule 2 say? The one with the least amount of formal charges. There's 1 formal charge, 1 formal charge. We have another tie. So we have to come up with a third rule. The third rule, all things being equal, meaning the first 2 rules, a structure with a negative charge on the more electronegative element will be more significant. So what are we looking at? We're zooming in on a negative charge on an oxygen and a negative charge on a carbon. Which element is more electronegative? Oxygen. So that rule says that negative charge on the more electronegative atom is going to make that the most significant. Now let's think about that for a minute. What does electronegativity mean? If we put it in layman terms, we can say electronegativity simply means that the atoms that are more electronegative want or can handle a negative charge. Right? So when you compare oxygen to carbon, oxygen's like, yeah, bring on that negative charge. It's not going to affect me as much as it's going to affect carbon. So if you could interview carbon and oxygen, and the doctor puts that little pain chart, 0 through 10, oxygen will say, yeah, I feel like a 4, and carbon's going to be like, yeah, I feel more like an 8. Okay? Because this is all about stability. Why would a molecule want to be in a resonance structure that's high in energy and very uncomfortable? And so it's going to be more looking like the more significant resonance structure. Okay? Now let's take this concept here and see if you can apply it to a problem. Okay, so I'm giving you a shortcut. The question is, which one of these is the most significant? So we are going to have a tie for the first rule and a tie for the second rule. So we've already done that. Now it's rule 3. Let me read it again. All things being equal, a structure with a negative charge on the more electronegative element will be more significant. Do we have a negative charge on this example? No. So how would you reason through it to come up with which resonance structure is the most? You have a thought? Yeah.
Would the oxygen without the positive charge be more negative because it doesn't have a positive charge?
Okay, so what you need to focus your attention on, let's not worry about oxygens that are neutral. If I understood your question right, you have to focus on this guy and that guy. That's the comparison you're going to make. Yeah.
The one that's least electronegative?
The one that's the least electronegative. So which one do you think is more significant then? The one on the right or the one on the left? The one on the right. Yeah, so that is the most significant. Okay, now let's think about this logically here. Between those two atoms, nitrogen and oxygen, which one's the more electronegative atom? Oxygen. So it wants negative charge, but what does it have? Positive charge. Right? And because it's more electronegative, it's going to feel a whole lot more hurt when there's no electrons around. So if this is oxygen, this is nitrogen, oxygen's painometer is going to be around 9 or 10, and nitrogen's going to be less than 10. Because it's less electronegative, nitrogen is less electronegative, so it can handle a positive charge better than the more electronegative oxygen. Alright? So when you look at these two examples again and study that out, you'll see that we cannot use the exact verbiage where it says all things being equal, the negative charge is going to be on the more electronegative atom. That is true when there is a negative charge, but when there's a positive charge, you have to think a little bit differently about that process. Does that make sense? Okay. And then the fourth rule. Okay, the fourth rule is basically we're just throwing our hands up. If we have a tie again, after going through rules 1 through 3, we just say, screw it, they're all the same. Okay, so for example, if we have carbonate here, let's see, negative, negative, and I'm doing this a little faster now. Okay. Negative. I'm not drawing in the lone pairs, but you guys know how to do formal charges, so you guys can figure that out, right? When you take a look at those three resonance structures there, you go through rule 1, they all have an octet. Rule 2, they all have the same amount of formal charges. Rule 3, the negative charge is on oxygen atoms in each 3 of those examples. And so at that point in the game, when you find a 3-way tie, you're just like, they're all the same. So what we do is just say these 3 resonance structures are equal contributors. They contribute to the resonance hybrid the same. So what we have to do is be able to take a look and draw resonance hybrids. Okay? And the way that we draw resonance hybrids, let's do this one right here. Clean this up a little bit. So what does the resonance hybrid look like for this guy and this guy? So how you're going to start this out is just draw all the bonds. Well, draw all the single bonds. Ignore lone pairs, ignore double bonds. So the resonance hybrid here is going to look like this. We have a carbon. Okay, and an oxygen. Do you see how I got rid of all the double bonds? Right? Make sense? Now, when I take a look at this structure on the left, I see a double bond between these 2 carbons. But then on the right side, there's no double bond. So when I come up to my green structure, what I'm going to do is just do a dotted line to represent that there's a partial double bond. Because remember, these two resonance structures in purple, the molecule doesn't say, hey, I want to look like resonance structure A, and then in a split second it converts to B. It doesn't do that. It looks like the resonance hybrid, and that's what we're trying to represent. Now I see a double bond here between oxygen and carbon and a single bond. So that means that there's a partial double bond between the carbon and the oxygen. Now we have the partial bonds so that's good. But now we have to look at the formal charges. The oxygen atom has a full-blown negative charge, and then it's neutral. So what do? We draw a delta symbol, Greek symbol delta, which just simply means partial. Is that going to be a partial negative or positive? It's going to be a partial negative, because we see it's negative here, neutral there. And then we go to the other chart, that carbon's negative, that's neutral. So we would just go another partial negative right there. Okay? Now, could we complicate things a little bit more? Of course we can. Could we draw another resonance structure? What if I say, let's take these lone pair or that pi bond and move it right here. So now I could draw it like this. All right, that's a valid resonance structure. I didn't break any octet rules. I didn't break any rules that you've learned up to this point. But now that resonance structure doesn't contribute very much. Okay? And why doesn't it contribute as much as the other two? We could use rule 2. Formal charges. This guy has 3 formal charges, and this one only has 1 formal charge. So that one on the far right is the really least significant. But what do you notice? That carbon has a partial positive charge. It has a positive charge there. So what we can do is represent that partial positive on this carbon. But here's the trick, and this is very subtle. Because this is the least significant, that means that partial positive isn't going to be there as abundantly as the partial negatives. So the way that we represent that is, let's exaggerate this so we get this point across. Because the first 2 resonance structures are the most significant, we're going to put a large partial negative. Okay. Well, let me take a step back. Let's analyze this a little bit better. Okay? When we look at these 2 resonance structures, what did we say? B and C. Okay. So A is the most significant, this is the second, and then the third one's the least. Since that's the most significant, this structure right here, where's that negative charge at? The oxygen. So what we're going to do is draw a very nice big partial negative on that oxygen. But then in the second resonance structure, the negative charge is on the carbon. But that's not the most significant. So we're going to draw on the resonance hybrid a smaller delta minus to help illustrate what the resonance hybrid looks like. And then when we come to the least significant resonance structure, we see a partial positive on the carbon. And so we would have to draw that even tinier. And so the sizes of your delta indicate to the reader where most of the charge is or isn't. Does that make sense? And so what does this molecule here actually look like? It looks like that. And we can't really visualize that on a piece of paper. Okay? There are computer programs that can look at the electrostatics of everything, and it helps. But that's the resonance hybrid. Okay, and typically we put the resonance typically in brackets like that. Okay. Any questions up to this point?
I have a question.
Yeah.
I saw that in your video, when you use the brackets, you put like the positive charge outside the brackets. When would you put it outside the brackets? The positive charge.
Well, when I put it on the outside, that's just generally just saying the overall species has a positive charge to it.
Okay.
Okay. But in this example here, I'm digging a little bit deeper. It's like, well, where are those charges?
Okay.
And to what degree do we feel those charges? Okay. So yes, my video kept it simple, but now in class we took it up a notch. Okay, let's see, it's 11:33. Okay, it's apply time. I'm going to give you three structures here. Okay, I'm going to call these A, B, and C. I want you to rank these from most significant to least significant. That's how I want you to rank them. Okay, you can ask TAs, they'll guide you, you can talk to neighbors. Let's see what you come up with. I'll give you a few minutes to see what you come up with, okay?